Okay, so what we are going to do today, it's going to be something like I'll try to make it light because you might want to, worried about the exam more than just study or take something new into your brain at this point. So we are going to talk more about waves, right? Which continuation from what we did in the previous two lectures. However, now we are going to look at the aspect of something else, like more physical, right? Instead of mathematical. So what we have been doing in the past two lectures was like looking at its mathematics. So we started out from simple harmonic motion and then get it connected to waves generation. And then we try to use mathematical description to explain the behavior of, and it's not behavior yet, it's like the characteristic of waves, right? So we can define wavelength, amplitude, period, frequency, how fast it travel, the elements that is oscillating up and down. So it's going to be like a displacement, velocity, and acceleration. Everything is sort of like beautifully described in a single line of equation. Does that sound okay? Like I sum up everything that we have done. Okay. So what we are going to learn today is we're going to look at some other aspects, especially we're going to start with energy. Even though we are not trying to calculate energy from the mathematical description, just like last time, we're just going to look like past it. Just like, okay, guys, just let's say that we have a source that give off waves and everyone now understand that the energy comes along with those wave propagation. So we're going to look at one particular type of waves today, and it's sound. Okay, so we just take a look at it, how it is, and then we're going to define how energy from the source get propagated without looking at the detail of the mathematical description. Sinusoidal waves, we throw it away. We're just going to look at more collective waves, yeah, more collective description of it. So we're going to define intensity and intensity level. So we're going to clear things up, what these two means and what kind of like usefulness of this whole thing. And once we're done with that, we'll look at one phenomena of sound waves, and actually it doesn't have to be sound, it can be any waves, which is Doppler effects. Okay, so we are going to look at that and how can we calculate stuff about that. And maybe next week after you're done with the exam and everything, so we'll talk about interference of sounds, and that will be later, right? Not for today. Okay, so main things today, I'm going to show you two things, and once it's done, it's done. And you guys can just get yourself ready for the exam. So we discussed a little bit, sort of like briefly last time, that sound wave is a longitudinal. So what does it mean by longitudinal? Now we sort of, all right, guys, understand this one very easily, that the medium oscillating back and forth, okay, in parallel direction to the propagation of wave. Okay, and then we already knew that we can use the same simple harmonic description to describe the oscillation of the medium. And for the sound, the medium is just air. That's it.
Okay.
It's simple. So every time that things vibrate and it's interact with air around it, it will just push and pull. It's not really pull the air, but it's sort of like it's vibrate and it's interact with the air molecules. And then the air molecules change its location. And sometimes things go like this. For example, when the air molecule gets squeezed, so it's get closer to its friends and neighboring atoms. So you get a part of the air that get compressed a little bit. And of course, when that source is sort of like retract back, you create a void, like something that's kind of like there's a vacancy open up. So you have a rarefaction portion. So it's like a portion of air that get less compressed, or the pressure is reduced from regular pressure. Does that make sense? And if the source keep vibrating forward and back, or forward, backward, you start a pattern of compression and rarefaction, and that thing will just keep propagating out. And when this compressions, or you can think of it, the change of the pressure that is changing, reach your eardrums, then it's going to vibrate your eardrum, and then your brain will interpret what are you hearing as sound. Okay, so that's a whole concept of things that making sound. So every time that you you interact with the air, all right, you clap your hand or snap your fingers, whatever. So you do something with the air. And every time that there's when you do like a micro, it's not doesn't have to be microscopic, but when you do it in close sort of like observation of the thing, you generate something that is actually some vibration going on. So the sound will just generate from it. Okay. So you can think of sound waves to be a pressure wave. And the disturbance that we have been talking about is just the disturbance of the air pressure. Does that sound reasonable? All right. But anyway, when you look at this one on the right, you can see that as long as you assume that the source of that sound is vibrating in a simple harmonic fashion, so let's say it has a single frequency, then you're going to generate sine and cosine function wave. So whatever that we have learned last time, sinusoidal waves function and everything works. Okay, even though this one is a longitudinal wave. Is it good, guys?
Okay.
So that's it. So there's nothing to worry about. You can even use sinusoidal waves to describe the displacement of the air molecule itself, or you can look at the pressure that is changing. Of course, the pressure change will be sinusoidal as well. So it will look sinusoidal, even though the phase, the location of the wave might be displaced with each other a little bit, but that's all right. Okay. So I'm not going to dive into this anymore because I think we're done. And it turns out when we try to look at the change of the pressure, things get complicated for no reason. Yeah, there is a reason for it. Sorry. There's no reason. There's a reason for it because you have to deal with the property of the air. And then you look at the elasticity of the air because you need, think of it like a jelly-like. So something has to oscillate back and forth. And then the mathematics get complicated because you have to study another property of air. So that's why I decided to, all right, just let it go. That's not very fun. And you're going to spend, quite some time to understand the behavior of the air in the elastic mode and all this stuff. So don't worry about that one. So what we are going to look at this is just jump right into it, guys. So let's say you have a source right in the center. And let's assume for simplicity that this source is just generating sound. So even you have something vibrating, or you can think of it like a speaker, but this speaker is like a point speaker. So it means it can generate sound in all directions. When you talk about all directions, it means the wavefront. When I say the wavefront, mean if you track any points that look alike on the on the wave, but this wave is now in 3-dimensional, is going to give you a spherical surface. Does that make sense? Okay, it's just like you generate a source. You have a source that's generating a wave, but it's at the center of it, and it's generate waves in all directions. So the surface of that wave, if you try to follow or track that wave, is going to have a shape of a sphere. Does that make sense? Okay, so let's say that this source can generate power, which is, everyone know, is just a energy per unit time, right? That's the definition of power. So you think of it like this source of wave has power delivery. So it has sort of like a delivery rate, the rate that this source can generate energy, all right? And it's dissipated through waves. Think of it that way. So what it means is now you have power of the source defined or sort of like assigned. Then the wave will just propagate it out in a spherical manner. Now, when you get larger and larger in the surface of this wave, or that means if your observation point is far away from it, let's say around down here, well, I want to observe the sound, or it could be any wave actually. I would like to observe the waves. You look at this one, and then you are sitting on the surface of the sphere that looks way bigger than it's originated from. Does that make sense? So that means if you said that this source give off the energy E, but it has to distribute across the whole surface. So if the surface is still small when you are close by, then the energy per unit area will be quite big because you have a very small area to distribute this energy around. But once you get further away, the spherical surface is getting larger. So the surface of the sphere is getting bigger. So the energy per unit area is going to be smaller. Does that make sense? Right? Because now you have more area for this energy to spread out uniformly. And that's what it is. So physicists decided to give it a definition of this. It's a power per unit area. That's it, guys.
Okay.
Introducing intensity. Is that simple? I don't know if I'm talking sensitive to you or not. And just I was kind of sick for a couple of days. So it's okay now. Right. Monday was better. But I don't know. Today is kind of like getting really kind of like blurred a little bit. All right. So what you have over here is power per unit area. And because you can express power as energy per unit time, so it means it's just the energy per unit area per unit time. Okay. And because right now you assume that the source is just a point, so the surface area, you can sort of like, use the expression for the spherical surface area 2 pi r squared. Put it in here. All right. But of course, if it's not a spherical, you just keep it as any area that the energy is being distributed across. Sounds good? All right. And this is one reason why when you are walking away from a speaker, then the sound from the speaker getting quieter. Is that because the intensity getting lower? That's why. Okay. So that means the loudness of sound that you perceiving is directly proportional. Well, not yet, not called directly yet, but it depends on the intensity that you observe. Okay. The larger the intensity, the louder the sound. Okay. All right. So that's what it is. And now you can see that it's 1 over r square factor. So that's how it's going to get quieter over time. I mean, but when we say quiet or not, wait for it, we might have something else for this. But at least if we talk about intensity, then it's 1 over r square factor. Okay. All right. So that's the conclusion. So with that, then things is quite easy to calculate because now it's purely maybe geometry or it's just calculations using those formula. Look at this example. You have a fireworks rocket explodes at a height of 100 meters above the ground. So you have some explosion going on here, 100 meters above the ground. And you have an observer on the ground directly under the explosion. So there's some dude right here waiting here, experiences an average sound intensity. All right, so this guy said, all right, I can observe the sound intensity of 7 times 10 to the negative 2 watt per square meter. And he experiences for 2 seconds. So let me write it as a delta T, the amount of time that he is sort of observing this sound. The question asking, what is the total sound energy from the explosion? All right, so think of it, this is like a one way that you can determine sort of like how big is the bomb. Think of it that way. Does that make sense? Right, because you can, all right, I'm just gonna sort of like, collect the sound, and if the bomb is big, it means the sound that is generated is supposed to be big along with it. And then you can probably do some estimations, what type of bomb or how many kilograms of, ingredients that use in the bomb or something like that. All right, roughly. Okay, so you can trace back to calculate the energy of the source by using that expression right there. Intensity is power per unit area, but because right now we can assume that the source is just a point source. So you can use 4 pi r squared to be your area that this energy get distributed. Okay. And then because the power itself is just the energy per unit time, so you can express that power as a ratio between the energy delivered divided by the amount of time. There you go. And from here, then you can calculate the E, the energy from the source. It's just going to be the intensity times the whole surface divided by, not divide, sorry, multiply by the delta T, and you are done. Does that make sense, guys?
Okay.
Simple enough. Yes, yeah. Not a lot of mathematics, no confusion whatsoever. All right, so all you need to do is just plug in the numbers. Intensity is already in SI system, perfect. Watts per square meter, that's good. 4 pi, the distance from that source to the observer is 100 meter, perfect. Just put it there, square that. And times the time, amount of time is already in second, just put it there. That's it, guys. You are done.
Okay.
Okay, not bad. So the concept of intensity is straightforward. All right. Once we define it's just a ratio between the power per unit area, it's done. Now, try again. Okay, let's do some common question that's pop up in physics question or in other kind of question all the time. It's when you want to compare between two scenarios. Look at this. You have an area of a typical eardrum. This is pretty realistic, which is about 5 times 10 to the negative 5 square meter. Calculate sound power incident on an eardrum at, now let's introduce this kind of like good to know numbers right here, is the threshold of hearing. It's on average. Human starts hearing sounds when the intensity that fall upon the eardrum is about 10 to the negative 12 watts per square meter. All right, cool. So this is numbers that we're going to take and use it. So they want to calculate the sound power. So you are directly applying power is just I times A. Does that make sense, guys? Simple. Just sort of plug it in. Okay, and then just say 10 to the negative 12. Let me omit the unit here. And you just times the area. At the end, you know it's going to be in the units of watts. You are done. Cool. All right. Another number that's sort of like good to know, but don't have to memorize it. It's called threshold of pain. So at this level of intensity, you will start to hear, you start to feel pains in your ear. And it's about 1 watt per square meter. So let's calculate the power there. So this threshold over here is going to be the product between the power 1 watt per square meter times the power, the surface of the eardrum, and that's it. Okay, which is not a lot actually. It's like 5 times 10 to the negative 5, but because it's a delicate part in your body, right, you're not supposed to be able to put a lot of power into it. Your eardrum probably just pop and all this stuff. All right, but anyway, the point is this. Look at these numbers right here. The range or the order of magnitude is huge. See that? Notice that? You're going from 10 to the negative 12 all the way to 0, let's say. So that's like 12 order of magnitude. Wow, that's huge. Okay, so not many things that actually can range across this much of more order of magnitude. All right. So this related to something else that we are going to discuss, but the concept of intensity related to power and the surface area is done. This is it. Next. Now there is a problem. So when you talk to your friend, okay, and if you have only one friend that's talking to you at the moment, then you probably hear the sound, the loudness of the sound at one level. But then when you have 2 of your friends talking to you at the same time, the sound is coming out is going to be louder overall, right? But let's say you have like 100 of your friends talking at the same time. My question is, do you hear the sound 10 times louder or not? That's a question. But then, of course, 10 times may be harder for you to detect anything. So let's say that you go to a concert. Now you have 10,000 people screaming at the same time. So the question is the sound that you're hearing is 10,000 times louder than only single person screaming at you? What do you think?
Okay.
Does that make sense? The question is like, if there's one person screaming at you and you have 10,000 people screaming, all right, even though you cannot put 10,000 people like, very close by at the same distance. But anyway, you think that the level of the sound that you're hearing is also multiplied 10,000 times? The answer is no. Okay, it turns out it's just like your ear does not respond to the intensity of the sound that gets into the eardrum linearly. Does that make sense? Yeah, it's not, because you can see, like, go to your concert. I mean, you still not like, tears off your eardrum or anything, right? You can go even like super big, like, I don't know, super crazy, Rachamankala, whatever, like 50,000 Toon Body Slam concert or whatever. Yeah. But everybody like go crazy. But I mean, you still not, I mean, all right, you maybe it's loud, but it's not like 50,000 times louder. So that's what it is. Your perception of sound is non-linear, guys. It turns out it's non-linear. That's the fact. Even though it's not like super duper like perfect, it's not like computerized eardrum or anything, but on average, from the collection of data and everything, experiments that scientists whatever has already collected the data, it's non-linear. And every time you talk about non-linearity, what kind of function you think of? Yeah, very good. Whatever
Okay.
you're thinking is correct. It's logarithm. So you guys remember log of 1 is 0, log of 10 is 1, log of 100 is 2, log of 1,000 is 3. See? So the property of logarithmic function is just trying to convert or transform something that's grow exponentially, but put them in a linear change. Does that make sense? Okay, so every time you take logarithmic function, and if that logarithmic function has some sort of like exponential behavior into it, then you can just convert that into just like numbers 1, 2, 3, 4, 5. And because right now we would like to work under the 10 to the power stuff, so that's why we use the base 10 log. Okay, so we're not going to use like natural log ln, we just use log base 10. And the good thing about this one is now what you want is just you want to make like a comparison, because you say that, hey, if whatever things changing is non-linear, all right, how bad is it? Or I mean, how are we going to, sort of like trace those changes? So what you're doing is just you do the comparison. Look at this one. This is what we want. The one that we're going to use in the formula is this. We want to use the ratio between the intensity, that's the one where we just defined, relative to the intensity not over here. And this is the threshold of hearing that you just saw. And we just saw from that is about 10 to the negative 12 watts per square meter. All right, so just take the ratio first. You want to know what is the intensity that you obtain relative to the threshold of hearing, how many times. Once you have that, because you know that whatever you hear is not going to be linear, you just put the non-linear term into it. You take log of that ratio, which is perfectly fine because the ratio will give no unit. Log of something that your new unit is going to give you just a number.
Okay.
And once you have that, we're going to have a quantity, and that quantity, which is just a number, is in the unit of bell. Here we go. You start to get a clue what I'm going at. And then because once you get the units of bell, the unit is a little bit too coarse. It's like you want like a finer level, separations. You want like, put things in more refined scale. So you times 10 and divide it by 10. Once you divide it by 10, that extra 10 over there, I'm just going to put it right here by 10. Guys with me? All right, so I have 10 in the front and 10 down here. And this 1 over 10, that is the deci, 10 to the negative 1. So that's why this formula right here is the formula that's giving you something we named sound level. And it's in the units of decibel. I think the one that you guys familiar already. Yeah, every time that you measure sound, it's in decibel. So now I hope that you understand what is measuring. It's actually measuring the intensity under the log scale with the 10 factor in it. Okay. Plus, actually, the full name of this one is called intensity level. Intensity level. But because we already defined the intensity, and to talk about this, it's kind of like, long word that you have to talk, like speak out, like intensity level. So to be able to distinguish between the two, most of the time people just use level to refer to the intensity level, and just use intensity just for the eye, just the intensity. All right, does that help?
Okay.
Okay, so whenever you have the keywords level, think of intensity level, the beta. So we use the, we can pick a symbol right there, just the beta. And once again, confirm the threshold of hearing is not a constant of the universe or anything. It's just the agreement or average. This is a number that has been averaged for a long, long time, and it's all over the world. People just agree that, okay, that's about it. 10 to the negative 12, that is the threshold of hearing. Okay, so one thing that you have to now understand right away, 0 decibel doesn't mean that there's no sound. The 0 decibel is just the threshold of hearing. That is when you start hearing something. That's a 0 decibel. Okay, and now normal conversation is already up 5 orders of magnitude, so it's already 50 decibel approximately. When you are at the, out on the street, the busy traffic sound, that's already 80. When you go to a concert, that's super loud, that's 120 decibel, but still fine, right? Your ears get numbed a little bit, but you go home, wake up, everything is good. But then you're operating some heavy machinery, right? Now that's gonna get very, very, super loud. That's why you need like a protection, okay? That's to be safe. So those construction workers with the machine, well, this is machine gun, so it's in, probably not constructions, but just to be not talking about something violent here. All right, but anyway, so heavy machineries usually generate a super loud sound, so you need some sort of like, protection there. And when you're nearby the jet airplane, that's already 150 decibel, and that could hurt your ear, right? You can make your ear bleed there if you stay very close without any protection there, something like that. Cool. So this is sort of, I hope that's what it is, and that's just definition. So the rest, just take a look at some examples and it's done. Is that cool? Sounds like
okay.
I would say like super different from what we did with like sinusoidal stuff, right? Just like, kind of cool and plain. All right, let's take a look at this example. Two identical machines are positions the same distance from a worker. The intensity of sound delivered by each machine at the location of the worker is given. All right, so this is your I intensity. Right? There's no level or anything. Plus, look at the unit. It's guaranteed to be intensity I. Find the sound level heard by the worker. When the machine is operating, only one. So there's one machine running. So that's easy. Let me call like a beta sub 1. So beta 1 right there is 10 log. You take the intensity that you want to calculate, 2 times 10 to the negative 7 divided by the threshold of hearing intensity, 10 to the negative 12. The units cancel. So what you get over here is going to be 10 log 2 times 10 to the 5th. So far, so good. All right. From this point on, you can actually punch the calculator or whatever you like. But what I'm going to show you over here, just give you a quick manipulation of the log. If you remember, log A times B is going to be equal to the sum of two logs. All right, this one's familiar, yeah? And the log of the ratio is going to be the subtraction of the two. Cool. All right, so over here, actually, I can sort of write it out a little bit, and there is a 10 log 2 plus log 10 to the 5th. And log 10 to the 5th over here, this will give you just number 5. All right, just to leave it there. All right, I have a purpose here. All right, so my point is the final numbers that you're getting is going to be 50 plus 10 log 2. Just keep it there. I mean, you can punch the log 2.6, whatever, but I'm just going to keep it like that. All right, you don't need to do this. I have a reason I want to show you the contrast between part A and part B. Now, what happened when two machines is running? Let me call it beta 2. You do the same thing. So it's going to be log. Now, the thing is, the intensity based on the power of the source, right? And when we have two machines running at the same time, the power will double from in the source. So the intensity will double along with it. So what I'm saying is, in conclusion, the power go with the intensity 1-to-1. You increase power 10 times, intensity increase 10 times. You increase power 100 times, intensity increase 100 times. Same thing over here. So that means the intensity that you get when two machines are running is going to be just twice, just only a single machine running. Does that make sense? All right, so it's 4 times 10 to the negative 7. And then you divide it by threshold of hearing, just like before. Okay, so everything works just like the same. Go ahead. So it's going to be 10 log 4 times 10 to the fifth. And now you know the final answer. It will look exactly the same if I do the same manipulation here. See, that's the change.
Okay.
You got what I'm written there. So over here is just I'm trying to once again just emphasize what the beta is. The behavior of the beta is a non-linearity. As you can see, you double the intensity of sound. The beta only changed a little bit. You're going from 50 something to 50 something. Does that make sense? Okay. And that's why you can, have 10 machines running. The only thing that is going to change this to 20. Okay. And that's just, 50 something decibel, on and on. Does that make sense? All right. So it's not going to be 10 times louder, but it's going to be louder a little bit. That's what the beta is trying to reflect, the human's perceptions of sound. That's what it is.
Okay.
All right, guys. Sort of like not bad. Today is kind of light. Any questions so far? I think it's kind of like cool down. I would call this is like a halftime break or something. Because once we're done with this waves module over here, take the second exam, the last module will be the most fun to study. Yeah. With once again, with extra calculus, with no extra charge, just like before.
Okay.
Okay, guys, everyone try this. The sound level at the distance 3 meters from the source is given to be 120 decibel. At what distance will the sound level be 100 decibel? That's like a normal scenario. You might be staying too close to the speaker. If the sound is so loud, 120 decibel, yeah. So you want to walk away from it. But this question asking you how far you have to be if you want to, reduce the sound that you're hearing from 120, which is kind of like, it's too loud, down to 100 decibel. All right, give it a shot, guys. Right, try to up my spirit a little bit here. All right, guys. I'll give you this, like a couple minutes head start, maybe. All right, but the key point is now this final examples for these topics over here is just try to give you the connection from the I that we started out from and the beta that we just introduced. Okay, let me start by reminding you what's the formula we're using. The beta is 10 log I over I naught. Now, one big clue is this. You are dealing with two scenarios, two states. You have two things. You have, two whatever situation to compare. So the best way for me, at least, is try to write them both in a separate equation. So I can call this beta 1, I1. When you say 1, 1, 1, it means when this whole thing is at 120 decibel and you are 3 meters away. Let me call this the first scenario. Does that make sense? And then what you are going to compare with is, right, guys, then there is another one, like scenario number 2. You already move yourself further apart. So the intensity will be new, the new one. Let me call it I2. And then you see divided by the threshold of hearing intensity. Now you want to compare between these two scenarios. All right. What we got from the previous example, we just say, okay, we look at the number, they are different by a little bit. But now you really want to compare them. So the trick is when you have two logarithmic function, usually you don't do the product, you don't do the multiplication, or you don't do the division. Does that make sense? Because when you have two log and then you do log multiplication or log division, it seems like the manipulation of the log function is going to go somewhere, weird. But what you really want to use is the one that we just introduced over here. It seems like subtraction of the two log seems to be a very good one because your argument will get to be a ratio. So I'll show you what I mean here. Let's say if I take beta 1 and then I subtract out the beta 2. So what I'm getting over here is on the right side, I'm going to get log 10 log I1 over I naught. Subtracting out with there 10 log I2 over I naught. Looks good. And now I can pull out a common factor 10 And now I have log of the difference of log. So what I can do is I just say is a log of the ratio. You guys with me? So I get I1 over I0, that from the first term, divided by I2 over I0 from the second term. Cool. And now what you can see is your I0 just get canceled. So that those just, gone. So what you left at the end is just going to be here. Nice. Log of the ratio.
Okay.
Isn't that cool? So that's usually how you manipulate logarithmic function. That's what you do. You do subtraction or addition if you want to. But for us, we want to compare. And whenever you want to compare, before you want to take the ratio, you want to do like, P1, V1 over T1 equal to P2, something. But because you are under logarithmic function, you cannot just take the ratio. So that's why I take difference instead. So once you have that, then things is good. Because right now, the information it's given is not in intensity. It's given in the distance over here. So when you have a distance, the things that you think of is like, oh, Ajahn, that can go back to the ratio. So the intensity is going to be the power over the area. And we assume, because right now it doesn't say anything, so we just assume that it's a point source. You can use 4 pi r square. So you can actually separate them into whatever scenario you have. It can have its own power, it can have its own distance, whatever. But in our case over here, the good thing is you are comparing with the same source. So the power must be the same. So far, so good. All right. So I'm still keeping the ratio techniques. The technique is all about taking the ratio between the two. So my final ratio that I'm getting from here is, here we go, 1 over 4 pi r1 square divided by 1 over 4 pi r2 square. You guys with me so far?
Okay.
Okay. And now 4 pi just gone. No problem. Bam, bam. I can flip that r2 square up. So your final expression that can be used is going to be r2 over r1, the whole thing square. That's how you get the relationship from the intensity level, decibel, all the way to the distance r. You're going through the definition of the intensity, but then it's inside the log. So you do the difference between the two. So once you have this, now I'm ready substituting the numbers. Beta 1, that's 120. Beta 2, that's 100 decibel. 10 log R2. R2, that's what you want to figure out. R1 is 3 meter and the whole thing square. And that's it, guys. You are done.
Okay.
You can just rearrange this whole thing and then come up with the R2. Okay, sounds cool. All right, guys. So that is it for the first half of the stuff that I want to deliver to you. It's just 2 definitions so far: intensity and intensity level. Yeah. There's a question. Oh, yes. Question. P equal. The reason is the P1 and P2s are equal because you have the same source, just like you are walking away from a single speaker. So the speakers still give off the same power. You haven't changed anything. All right. But the way that I did the analysis over here, that's give you the flexibility for the futures problem, just in case that you might have the situation that, I mean, the source get replaced by another source and you also moving away from it, moving closer to it. So you have all the flexibility to do anything. Yeah, sounds cool. All right, guys. So if this is good, then we'll take a break right here. I think this is a good point to stop. And then I will talk to you with another phenomena that is very interesting. All right, guys. So see you in 10. All right. So the next concepts that I am going to introduce to you is the Doppler effect. I don't know, have you heard of this one? But it's something that is kind of like happens around you all the time. Every time that there is a source of the sound traveling, the perception of the sound that you hear is not going to be exactly the same as the sound when the source is generating in the stationary with respect to you. The easiest example is maybe cars or motorcycle, or maybe the siren sound from the ambulance that's just passing you by. The sound that you hear is go like, this is going to be the worst example that you've seen. All right. I used to try to use like a clip or something, but it's because of the zoom and everything, it doesn't work. So I just tried myself. It's just, that's what it is. So what you're getting over here is when the source is coming towards you, the sound is getting higher in pitch, right? The frequency is going up. It's like, and then it's when it's going away from you, it's going, or when you do like maybe F1, like Formula One, something like that. All right. So that changing of the frequency due to the movement of the source, that is the Doppler effect. That's it, guys. Simple. Okay, so what we are going to try to calculate here is just like what is going to be the frequency that we are sort of like observing. But then the thing is, maybe this is maybe unusual. There is also possibility that maybe the source is stationary, but you actually travel. The same effect will happen if you try to travel toward the source. Then the sound that you're perceiving is going to be higher in pitch. And if you're running away from the source, then the frequency will drop. Same thing. So that's why for these concepts, sometimes people think of like a relative velocity, because when you say the source approaching you or you approaching the source, I mean, they are pretty much the same thing. All right. Even though it's not exactly the same. However, I mean, people thinking about this in terms of the relative velocity. But before we think about that, today, I don't want to get to that topics of relative velocity, because some of you get confused anyway, even though it's a concept that you probably have done it before in maybe 101 or maybe some high school physics. But to me, it doesn't seem to work so well. You will see why in a little bit. Okay. So hear me out. What kind of like parameters or variables that we really need for be able to for us to be able to calculate the frequency that gets shifted due to the movements of either the source or the observer. So let's look at this scenario over here. This is it. So what do you need? First thing, you need the source for sure, definitely. And you need an observer. So you have S representing source, O representing observer. Cool. But then the source could be moving. This one, even though it's written as a stationary, but you should have the source has ability of, having possess some velocity. So I can call this velocity, but just to signify that this is the velocity of the source, I use the S subscript over here. Looks good. And then of course, the observer can travel. So you have velocity for the observer as well. So I use a subscript O for that. But then sound is a wave. So wave never stop. It has to move. So the wave itself, the sound wave, will also have its own velocity. Let me use just V without any subscript. Does that make sense? So what you are looking at right now is you are looking at 3 velocity. Okay. There is a velocity of the source, the velocity of observer, and the sound velocity that's always there all the time. You cannot change it. Okay. So that's what it is. So that's why there are at least 3, not at least, there are exactly 3 velocity. What else? The sound that generated from the source must have some frequency. So let me call that frequency from the source. Once again, I use the S subscript for that. And then you will have the frequency that gets observed by the observer. So I'm going to call it F sub O. Make sense? All right. And then at the end, if you really want to calculate the wavelength or whatever, you still always have this V equal to F lambda in your disposal. You can use this one all the time. That's linked between the speed of waves, frequency of waves, and the wavelength of the wave. Done. So these are the stuff that we are going to do. We are going to link, overall, what you are seeing over here is there are 5, 1, 2, 3, 4, 5 things over here. All right. But then at the end, it's very simple. I'll show you the structure of how can you calculate the observed frequency. That's our main role, guys. We want to figure out the observed frequency. And it turns out it goes like this. Blah, 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 blah.
Okay.
All right. I know you guys, some of you don't like proofs or verification or derivation of formula. And I know. So I just put this one here for your own reference. For those of you that really want to dig, deep dive into how to get to the formula, it's this page right here. However, to me, the scenario that we are looking at right now is so simple that we probably don't need to prove it. I'll show you what I mean here. At the end, what it's trying to do is trying to see what happens when the observer is traveling, okay? And then what will happen to the observed frequency. So they try to come up with, like, the wavelength that gets changes due to, but you think of it, the observer is going against the sound in this case. So when you go against the sound, if you're not moving, the sound will hit your ear at the fixed frequency, the same frequency as the source. Does that make sense?
Okay.
But then if you move against the sound, so number of hits that you're going to get to your ear is going to go faster. That's why you get a higher pitch. That's it. It's simple. Okay, so this means when you go towards the source, the number of hits will get faster than regular. So this means you have a higher pitch. On the other hand, if you're running away from the source, so the wave has to catch up on you. So the number of hits will get smaller in numbers because you're running away from it. So there are only two cases. Don't need to think too much. Does that make sense? It's either you going towards, you mean observer. It's either observer going toward the source or running away from the source. And you know the effect. If the observer running toward the source, frequency has to get a higher value. If observer running away from the source, frequency is supposed to drop. Simple as that. Okay, so there are only two things. Now, turn our attention to the other side. What about the source? So this slide shows you how to calculate, the change and stuff when source get traveled instead. But concept stays the same. If you are stationary, the source going towards you, of course, you look at the front of the wave. Because the source travel towards you, the distance between wavefront to wavefront to wavefront is going to get squeezed in because the new wavefronts get closer to the previous wavefront. Does that make sense? So if you're standing in front of the source, the number of hits that you're going to get in your ear is going to be larger than regular. On the other hand, if you behind, okay, I think I have another one here, scenario here. So if you have an observer stays behind the source, so it means the source is running away from the observer. Of course, the separation between the wavefronts will get further apart than usual. So the number of hits that gets to your ear is going to be smaller frequency. So that's why the pitch is going to be down. The frequency will drop. But when you look at these two cases, you have only two choices. It's either the source running away from you or the source running towards you. When the source is running away from you, the frequency will drop. When the source going towards you, the frequency will up, right? So that's it. This is the final conclusion without showing the proof or anything. This is it, guys. Look at the structure of the formula and you will see it's so simple. Look on the left. This is what you want. Is F sub O, which is the frequency that you get observed. That's what you want to calculate. And the structure of this equation look like this. You have like a big bracket over here or parentheses right there. That shows up in front of the source frequency here. Okay, look at that, yeah? So when you look inside the brackets there, eventually you're going to get a number. See? Because this whole thing will cancel out. There's no units. Whatever the numbers that shows up in that bracket will be, for example, not example, there are only three cases. If this number is larger, we'll say here, if this is bigger than 1, so that means the F observed is going to be bigger or frequency is higher. Does that make sense? Or it could be less than 1. If this bracket is less than 1, so it's mean the observed frequency will be lower in frequency than the source. Or it could be exactly 1. If that is the case, then whatever the source is, that's what you're going to observe. There are only 3 cases here. And then when you look at the structure of this equation one more time, look at this. That's sort of in a way that is something of like relative velocity, yeah, relative to the speed of sound. You can go either against or you can go towards it, on and on. But I don't want you to, I don't know, maybe that's my approach to these problems. But I don't want you to think in terms of the relative velocity all the time, because it might not work in some particular way. All right, but anyway, don't think too much about it. So I'm going to show you this. So what I'm going to do is give me an extra page here. And I hope if you guys agree with me, then it's going to be quite easy. But there, you guys probably wondering about what if I don't agree with you guys? If I don't agree with Ajahn, what can I do? Okay. All right. So I have the source on the left. I have observer on the right. Okay. All right. So let's look at the first scenario. Let's say if the source is going to your right and the observer going to your left. So in this case, they are sort of like moving heads on, like colliding each other or whatever. Okay. So what will be the observed frequency? So here, this is how it goes. The observed frequency is the ratio with relative to, or it's going to be the factor in front of the source frequency. And look at this, how I write this one down. The one on top is the speed of sound. And eventually you're going to have to compare with the speed of the observer. And down here is also the speed of sound, V. And it's going to be the speed of source. So the only thing that you need is just picking the correct sign. You see what I'm trying to get to here? It's just get the sign correct. And how many cases can you have here? If you learn it from probability theory, you only have 4 cases, because you have either left or right for the source and left or right or from the observer. So 2 times 2 is 4. So why derive things too much when the final results, there are only 4 types? Okay, here you go, guys. Look at this. Now the observer running toward the source. Should you hear the higher or lower frequency? Yeah, supposed to be higher, right? But then you look at this, the observer speed is on top right there. So you want the frequency to be higher, you put positive number there. Is that too easy? Now, look at the source. The speed of the source is V sub S. Now the source running toward the observer. What should be the final effects to the frequency? Yeah, we already discussed higher in frequency as well, right? But look at this. The speed of source is underneath. So it's the denominator over here. To have a final numbers larger, you want a smaller number here. So you pick negative sign. You are done.
Okay.
One more time. If the source running to your right side and then the observer running away, so it's mean maybe the source is catching up the observer or whatever. So the observed frequency will be, now you write down the structure over here. There, it's always like this. Now look at the observer first, V sub O. Observer running away from the source. When you determine this, you don't have to worry about is the source moving or not. I don't care, because all you care about is the observer running away or towards. That's it. So in this case, the observer running away. Running away, frequency drop. Drop means smaller number on top. I put a negative sign there. Now turn our attention to the source. The source running toward the observer. Running towards the observer from the source give the final result of higher frequency. But because the V sub S is underneath in the denominator, so you need to be not smaller in number, you pick negative sign. Done.
Okay.
Now you see what I'm at. Now the source may be running to your left, and then the observer running to your left as well. So in this case, source running away, and the observer is catching up. It doesn't have to be catching up as well, but it's going toward the source. So in this case, what will be the observed frequency? guys? Okay, well done. Just write down the structure. Yeah. The observer first. The observer running toward the source. The final effects will be higher in frequency, higher on the numerator. You put the positive sign in it. You get the numbers bigger. Now the source running away from the observer. Source running away result in lower in frequency. To get things lower from the denominator numbers, you add something to it to make the numbers bigger underneath. And you are done. The last case, you now can imagine if the source going to your left and the observer going to your right. So now they are sort of like separating, moving apart. So the observed frequency will be, you just write it out as structure. Okay. And then observer running away, frequency should be down. So you pick negative side on top. Source running away, frequency should be down, but because it's in the denominator, you put positive sign. And that's it, guys. 5 cases.
Okay,
You are done. I don't know you like this approach or not, but because we are looking at the Doppler effect in one dimension, so you have only 4 cases. It's either, it's in, out, in, out, whatever that's it. And things might be even easier if one of these two, either the source or the observer, is stationary. So some of these variable will go into 0. I mean, for example, if you have a stationary source, V sub S go to 0. Let's make it even easier. Okay, so let's give it like an application, and you will see how to apply this. Very simple, guys. Any questions up to this point? Looks good, sounds good. All right, okay, here we go. Right, now this is going to be use case of this formula right here. You have a train and is moving parallel to a highway with a constant speed of 20 meters per second. A car is traveling in the same direction. Okay, now you have a train traveling. Okay, boon boon. Okay, I don't think there is any smoke coming out anymore. All right, so there is 20 meter per second. 20 meter per second. There you go. Now a car is traveling in the same direction. Okay, so you have a car traveling in the same direction. 40 meters per second. Okay, cool. Now the car horn sound at a frequency of 510 hertz. Okay, so that's fine. So car which is like honk the horn, beep beep. Okay, and that is 510 hertz. So let me put some color over here. 510 hertz. And at the same time, the train whistle sounds at frequency of 320. Fine. The train doing something as well. So it's go all over the place over here. And the frequency of this whistle sound is 320 hertz. Here comes the question. When the car is behind the train, so that's exactly the scenario that I'm drawing right now, what frequency does an occupant of the car observe for the train whistle? Cool. You got what I'm trying to get to here? So now first you have to assign the correct role, right? Because one's supposed to be observer, one's supposed to be source. So in this case, they want to know what is the frequency that the occupants of the car observe. So this means the observer is here on your left. And the source is now the train. Okay, so this particular case, then the V source is going to be 20 meters per second. And the observer is going to be 40 meters per second. You guys with me? Because now the car is our observer here. Then go ahead. You want to calculate the frequency observed by the occupant in the car. So you take the ratio, multiply by the frequencies from the source. You do the V and VO, V sub and V observer, and V and V source. There. Now, let's pick. What should be the sign, guys? The observer running toward the source. So the frequency is supposed to be up. So that's plus. With me? Now the source running away, the frequency is supposed to drop, but because it's underneath, so you just go plus. Done.
Okay.
Cool. And that's it. The rest, just make sure that you substitute the correct number. So usually the speed of sound will be given, okay, like maybe like 340 meter per second on and on. So in general, so let's assume V equal to 340 meter per second. So this is sort of like an average speed of sound. It could be like 340, 345, 350, depends on the problems. So we just plug in the speed of sound plus the speed of observer is 40. In this case, is the car speed divided by 340 again, and the speed of the train, which is in this case for the source. And now, what is the source frequency? You want to listen to the train whistle, so it's going to be here. Your source is 320 hertz. Does that make sense? And you are done.
Okay.
And if you look carefully on the numbers that you're getting over here, you will notice something here, that whatever you get over here, this number is larger than 1. So that means you're going to hear a higher pitch if you are a passenger in the car. And the scenario looks pretty okay. Why? Because if you think back in terms of the relative velocity, the train is moving to your right with the speed of 20 meters per second. The car moving at the fastest speed, 40 meters per second. So from the point of view of the person in the car, actually the car is approaching the train. Does that make sense? So the car is actually catching up the train. So it's just like you getting closer to the train. So you're supposed to hear a higher pitch. So that makes perfect sense.
Okay.
Okay. All right. So that's cool. Now try again part B. Okay. Let me sort of squeeze in this number a bit. So get some space here. So I can split this in half. 320 hertz. All right, great. All right, good. With that. Now let's try part B. Down here. Okay. So now part B, after the car passes and is in front of the train. Okay. So now the car is already, oh, car looks really bad. There you go. All right. But it's still 40 meters per second anyway. And it's still horn sound, oh, green. There you go. Like that. Okay. 5-10 hertz. Same thing. No change. Nothing is changed. Now, what you have to do is right now, the question asking you to find the frequency does the train passenger observe the car horn. Okay, try again. So let me use the green color here. So for this case, part B, what is now your observer? It's now going to be the passenger on the train. So in this case, it's going to be S up here, and the observer now is the passenger in the car. Does that make sense?
Okay.
Yes, just so you won't get confused with the first one. I just use the green color over here. So now what you try to calculate is, what about the observed frequency? It's going to be the same ratio from the source. Set up the structure over here. Cool. And now pick the sign. Now your observer is the car. The car is going away. Is that right? Why? It's observer. Wait. I think I got this backward. Sorry, guys. They say, what frequency does the train passenger? So this is an observer here. Okay, sorry. My bad. Here we go. And source is now the car. Okay, cool. So now the observer is the train. So the train moving toward the car. Okay, so in this case, moving towards is going to have a higher frequency effect. So I put plus up here. Now, what about the source? The source now is the car. The car is going away. Going away, lower the frequency. Lower the frequency means higher number in the denominator. Yes. So it's going to be actually plus signs because it's actually the same scenario as the part A, except just switch the role between the observer and the source. Does that make sense?
Okay.
All right. So now let's sort of like substitute the number just to make sure that you got everything correctly substituted. What is going to be the speed of observer? It's going to be the speed of the car. Speed of the sound 340. What is the speed of the source? Now it's going to be, now am I writing it wrong all the time today? Sorry. Observer is 20. Sorry, guys. Speed of the train. My bad, my bad. And now the source is the speed of the car. There you go. And what about the source frequency here? Of course, it's going to be the horn sound. That is going to be 510 hertz. And that's it. You are done.
Okay.
Okay. And once again, if you notice, the value that you got from these brackets over here, as you can see, is less than 1. And as you can see from the part A, the mathematics will take care of the final result. The reason this one is less than 1 is because from the perspective of the observer, which is the passenger on the train, the car is actually running away because car is faster, 40 meters per second, and the train is just slower, 20 meters per second. So that's why the car is running away. So the frequency will be, does that make sense? So the frequency is dropped when the car is sort of like moving away from you. And that's it. It's done.
Okay.
Any questions so far? Sounds like doable problems. I think that's pretty much it. And this one just showcase how to utilize or how to apply this formula. And because once again, I'm not sure you like this approach or not, but seems to me like there are only 4 cases that you can apply. So it seems like it's just easy enough for you to just get your common sense up and running. Yes, that's easy enough to do. Okay. All right. However, there is one thing that is very very interesting I want you guys to try. And this is going to be our last exercise of the day. Sounds good? All right. It's going to be a very quick lecture today, but this one is super important and I can pretty much, like, let's say with the probability of like 80%, like this probably is the question in the exam. Because I don't know what else to give in the exam. If I show up like this, it's more like this is very close to plug and play problem. This problem right here, because all right, I mean, this is not super easy or anything. You have to know how to apply the Doppler equation a little bit, but it's still very easy once you identify source, observer, and everything. So it's done. Just plug in the numbers, you're done. This is more interesting, and this one has the actual sort of like applications of things that actually going to be very useful when you understand how this thing works. Okay, here we go, guys. Let's read through the question together and I'll give you a minute to think how to attack this problem. A bat moving at 5 meters per second and chasing a flying insect. So now you have a bat, okay, flying at 5 meters per second. And there is a flying insect somewhere here. If the bat emits 40 kilohertz chirp sound, so of course, bat doesn't have eyes, so they use the ultrasound, okay? So there's a supersonic and all this stuff, and just try to detect the echo from the objects around bat. So what it does is just send out the 40 kilohertz chirps and received back an echo at a different frequency. Cool. It right there. So the frequency that it's received back is 40.4. It's a little bit higher. At what speed is the insect moving and in which direction? Is it towards or away from the bat? And take the speed of sound to be 340, just in usual case. Isn't that cool? This kind of question?
Okay.
So this is definitely about the Doppler effect. The reason is because you kind of like can notice from the return frequency, it's different from the outgoing frequency, right? So whenever you have the manipulation of the frequency due to the movement of either the source or whatever the observer, that is Doppler effect. But how can we attack this problem? That is 1 minute of thinking right now. That's annoying, right? You don't have any concentration to think. All right. So in general, every time you do the Doppler effect, you need the source and you need the observer. But then from the look of this one is like the bat is both source and observer. So there must be something to it that allow you to do the calculation here. Isn't it interesting? And whatever you're thinking is correct. I am assuming that you guys sort of understand how this one goes. You have to break this into two halves. So what I'm saying over here is, in the first half, the bat side over here will be the source. And the insects over here will be the observer. So in that case, the bat will be moving. And because you don't know the direction of the insect, so you might assume that it's just going in some direction you don't know. Let me call it x meter per second. Okay, by knowing into your heart that eventually the mathematics will take care of the sign. So it's mean at the end, if the numbers that you solve and gone through everything and then you get a negative numbers, then you can tell that the insect's supposed to fly to your left. Something like that. Okay, so, or maybe you might give me an argument about Ajahn, because the reflected frequency is sort of higher. By common sense, you probably think of the insect probably want to go against, but who knows? It's totally depends on the mathematics. So I don't really know, but that just want to say that you can assume any directions to the velocity of the insect. That is fine. Okay, so the first half, what we get over here is the sound that coming out from the bat travel, reach the insect. So the insect will receive some frequency, which is going to be different from 40 kilohertz for sure, right? Because bat is moving, insects is also flying. So the frequency will be whatever. But then once it's done, you're going to get reflection. Okay, that reflection will flip the roles of these two. So it means the second half of this, what you're looking at is now your insect will be the source and your bat will now be an observer. However, whatever that you observe from the first half, so it means there's an observed frequency at the insect, will be used to be the frequency from the source in the second steps. Does that make sense? So just to be able to distinguish between these two sections, let me call this S prime, and O prime. So prime, just say that's the second half. So in the second half, the reflections will be the source, and eventually that sound will just travel back to the bats. So the bats will be the observer in the second half. Okay, so the extra condition that we have over here is these two are exactly the same. Whatever the insect hearing in the first half of this calculation will be used as the source for the second half. Cool?
Okay.
Let's go for it, guys. Let's talk about the first half. What I want is I want to calculate the observed frequency structure right here. Ready? There you go. Now look at the first half. The bat is the source moving toward the insect. The frequency is supposed to be, oh, I'm sorry. We start with observer, right? Sorry, my bad. Observer first. The insect, we already set the insect to move toward the source, the bat. So in this case, the frequency is supposed to be higher. So you pick positive sign here. Okay, now let's look at the source, the bat. The bat is moving toward the observer. So the frequency is supposed to be higher as well. But to get things higher in the denominator, you just get the negative sign. Cool?
Okay.
Alrighty. Now, just to make sure that you got this one right, let's substitute the numbers. Okay, velocity of sound 340. Speed of observer has to be x. You guys with me? Because now in the first half, the observer is the insect. Underneath 340 minus the speed of the bat, and it's 5 meters per second. And then the f sub s, the frequency of the source, it's going to be 40 kilohertz. There you go. You are done for the first half. But of course, you still don't know how to deal with this because we have two unknowns, f sub o and the x. Let's move on to the second half. Now, in the second half, you want to calculate the observed frequency at the end, the O prime. And you know this number is supposed to be 40.4 kilohertz. You guys with me? Right? That's the final frequency that the bat received the echo. You equate that to, once again, you set up the structure, V sub O prime, V sub S prime, and F S prime. That's for the second half. Now look at the second half, the blue. The observer is the bat. The bat is still, I mean, if I draw the velocity of the bat is, I mean, it's still flying to your right. So right now, the observer is going toward the source. Going towards is increase in frequency. So it's going to be bigger number up top. Now, what about the source? Now the source is the insect. So the insect now is going toward the observer. Going toward the observer is higher in frequency. Higher frequency means smaller denominator right there. All right, just to make sure that we get everything correctly substituted. So I'm going to show you what numbers are. 340, that's for the speed of sound. What about the observer in the second half is the bat. So it's going to be 5 here. With me, guys? Okay, so far so good.
Okay.
Down here, 340 minus the speed of the source. The source now is the insect. That's x. Now you are multiplying the f s prime, but we just already agreed that this f s prime just exactly whatever the observed frequency from the first step right here. So what I'm saying is I'm just going to take the whole expression here and plug it in here. Does that make sense? Okay, so what I'm doing over here is just going to take the whole thing, 340 plus x minus 340 minus 5 and 40 kilohertz. And that is it, guys.
Okay.
As you can see, the final equation only has this is x. And then you can finally solve for x and you are done.
Okay.
Okay, not bad. So I hope, I think I like this one because it's not too complicated, but it's just like, you know, a little bit tricky in the sense that you just have to break this calculation into 2 parts. But each part is still just like a simple Doppler effect calculation. All right, but what is the application of this? And if you notice this one, this is how you can detect the speed of the object at the distance without touching it. Isn't that cool?
Okay.
So this is what happens. If you want to know what the speed of the insect, what you do is you sort of like put some wave into it and detect the change in the frequency from the echo. So the wave that you use doesn't have to be ultrasonic, just like in the bat's case, but you can do with the laser beam, or you can do with whatever waves and all this stuff. And then the reflection will get you a different value. And that's what the police that give you the speeding tickets, that's what it is. They shine the laser gun on you and they try to pick up the echo from the car, and then they can detect the frequency change. All right, that's how it is. Okay. Oh, there's a question comes in. Okay. So about the direction of the insect. No, I don't know. I don't really know is the insect moving towards or away from the bat. But here is the final answer. If this x is positive numbers, so it will indicate that my assumption that the speed of the insect point to the left seems to be the good one. Okay, make sense? However, if I get this x to be a negative number, it's just saying that the velocity of the insect is supposed to be opposite. So in that case, the insect will travel to your right. So this one you can assume left or right, up to you. Okay, does that make sense? All right. If you assume x to be pointing to your right, the sign that you pick over here will be different a little bit, but at the end, the mathematics will show out, will reveal what will be the final answer. Okay, cool. Don't have to worry about the direction of the bat in the first place. You can assume it yourself right away. Okay, so come back to the application. So this is what it is. So the way that you can manipulate things is just by, for example, if you want to measure the speed of your blood flow in your artery or whatever in your blood stream or anything, you can put the ultrasound to it, and then it's gonna reflect out from the hemoglobin in your blood and all the stuff. So that pickup of that echo change, the echo frequency change, will give you the speed of the blood flow. So anything that you want to detect, like the speed of things at a distance, that's how you use. It's pretty much like a Doppler effect. And the big thing is the reason that physicists know that the universe is actually expanding is because the Doppler effects as well, even though it's not the Doppler effect in sound, but it's the Doppler effect in electromagnetic waves. For example, if you still remember from chemistry or in physics, you know that, for example, hydrogen will give off spectrum, right? So there'll be a spectrum from the hot hydrogen gas. It will give you like maybe the blue, the green, the red lines, all the stuff, and you know exactly what kind of frequency you're supposed to get. But then somehow at the distant stars, they also have this hydrogen gas. But then when you detect the spectrum from that star, it turns out the frequency of those spectral lines are not exactly at the same frequency that you measure on Earth. From that, then there is a shift. And it turns out it's a red shift. When you say red shift, mean it's lower in frequency. And from what we understood right now, it's just like, oh, something that's lower in frequency means it's moving away. And this is the reason why we can give a conclusion that universe is expanding. Yeah, because the signal that coming from the distant stars, they're all doing the redshift stuff. Okay, so things running away from each other. That's what it is. Is that cool? All right. So I hope this will give you a nice conclusion and some applications and just give you a very, very, I would say, easy to treat. All right. This is an easy treatment that you can deal with the Doppler effects problems, and then no need to worry too much about it. And mathematics is sort of like not too complicated. All right, guys. Sounds cool. All right. And I hope you guys don't mind that I don't do any proofs or anything. But I'm just decided, I think this is simple enough for you to get all 4 cases that's possible in Doppler effects. All right, guys. Any questions? I hope you learned something today. Cool. All right. If no questions, then I will see you guys on Saturday morning. Yeah. So I will be around from maybe 8 something and then until noon. And then at noon, the exam paper will be released then. Okay, guys. So take care and I'll see you guys on Saturday. Okay. Bye-bye.